So we've already talked about molarity as a means of representing the concentration of a solution, but molarity is not the only way. It turns out there are many ways to represent solution concentration, and we're going to talk about a couple of the other ones in this video. Right, this is a list of the other concentration units that we're going to talk about. And it looks like a lot at first, but I think you're going to see a lot of these are pretty closely related. Now, you may be asking yourself, why are there so dang many ways to represent solution concentration? It turns out that for different applications, these different concentration units are more or less useful. Just as an example, molality is one of the ones other units of concentration we'll talk about. Right? Unfortunately, similar name to molarity, just replace the R with an L. The difference between these two, in molarity, the denominator is the volume of the solution, whereas in molality, the denominator is the mass of the solvent. Molality is useful when we have temperature changes. You can maybe see why molarity isn't useful when we're changing the temperature, because while the moles of solute won't change when we change the temperature, the volume of the solution will. Things tend to expand when we heat them and contract when we cool them. So if we're talking about temperature changes, the molarity actually changes as the temperature changes because the volume of the solution is going up and down. And so molarity is useful when we have temperature changes because the moles of solute don't depend on temperature, the mass of the solvent doesn't depend on temperature, and so the molarity won't change when we change the temperature. So let's look at each of these a little bit more detail. Now, before we get into the other concentration units in more detail, I wanted to introduce something that I call Mike's table. And one of my friends and colleagues, his name is Mike, he introduced this table to me to help students organize the data when they're doing all these different concentration calculations. What can often be difficult in these concentration problems, we're given a whole ton of information, and it can be difficult to keep track of everything. And so by organizing your information in a table like this can help a lot. And so we have 3 rows and 3 columns essentially that we can fill out. So we have the individual volumes of the solute, the solvent, and the solution, the mass of each one, and the moles of each one. And so if I want to go from the volume of anything to the mass of anything, I know that density relates mass to volume. And so we can use the density to go back and forth between those 2 columns. Right? But in order to do that, we have to know the individual densities of the solute, the solvent, and the solution, because they're very often different. And then to go between the mass and the moles, well, we know we can do that with molar mass. And so we can go from the mass of the solute to the moles of the solute and vice versa, and the same thing for the solvent. Now, we can't go back and forth between the moles of the solution directly, right? Because a solution doesn't have a molar mass. It's a mixture. Now, another thing that we can do, if I want to know the total mass, all I have to do is add up the mass of the solute and the solvent. And I can do the same thing for the moles. If I want to know the total moles of the solution, I can just add the moles of solute to the moles of the solvent. I can't do that to the volume. So it turns out volumes aren't additive. If we take 50 milliliters of ethanol and 100 milliliters of water and mix those together, we don't get 100 milliliters of solution. It's generally going to be less than the sum of the 2 volumes that I started with, because those molecules can kind of get in there amongst each other. So I didn't put the plus and equals here because I can't do that. I can't add the volume of the solute and the volume of the solvent to get the volume of the solution. We'd either have to measure that directly, or if I knew the mass and the density of the solution, I could use the density to go back and forth between these 2. All right, so I'm going to introduce each of the concentration units in a little bit more detail. I have 2 quick examples as we're doing that, and then I'll finish with a more comprehensive example where we'll really make use of Mike's table. And then I have another video with an example using Mike's table as well if you want to see yet another example. All right, so molality is defined as the moles of the solute divided by the mass of the solvent, but we have to be careful on units again. The mass of the solvent has to be in kilograms. And so the units on molality, we can either report it as just lowercase m, like we would capital M for molarity, or we could report it as moles per kilogram. And so this is where the capitalization is important. Molarity is a capital M, whereas molality is lowercase m. All right, so I've got a quick molality example. I have 425 grams of my solute aluminum nitrate, and I'm dissolving that in 653 grams of water, and I want to know what is the molality. So the molality is the moles of solute divided by the kilograms of solvent. And so they gave me the mass of the solute, so I need to convert that into moles, so I need the molar mass of aluminum nitrate. So that's going to be 26.98. I've got 3 nitrogens. I have 9 oxygens. And so my molar mass, when I do that calculation, comes out to be 213.01 grams per mole. So now I can convert my mass into moles. So I'll take my 4.25 grams, divide that by the molar mass, and I get 0.01995 moles. I know I kept an extra significant figure, but that'll save me some rounding errors. So then the molarity is moles of solute divided by kilogram of solvent. So I have to be careful on units again. I've got 653 grams of water. I need that to be in kilograms. So we know that 1 kilogram is 10 to the third grams. So my 653 grams is 0.653 kilograms. So then my molality is the moles of the solute divided by the kilograms of the solvent. And my final concentration is 0.0314. And then I can either write that as moles per kilogram, or I could say that it's 0.0314 molal. Alright, the next units of concentration that we're going to learn are mole fraction and mole percent. And so mole fraction is represented by the Greek letter chi. And I've put here chi whatever because very often when we're talking about solutions and they ask for the mole fraction, they're talking about the solute. But there's no reason why we couldn't ask for the mole fraction of the solvent. So that's why I said whatever here, right? It's the mole fraction of whatever. And so the mole fraction is defined as the moles of whatever they're asking about divided by the total moles. And then a very closely related unit, the mole percent, just take the mole fraction, which is going to be a decimal, multiply it by 100, convert it into a percent. So mole fraction is a fairly easy concept, but we use it for solution concentration, and we use it for a lot of other things too. So mole fraction is something that's actually going to come up quite a bit in your chemistry careers. So it's good to get some practice with it. So just a simple example using mole fraction. And like with the simple example for molality, I didn't use Mike's table because in these simpler problems, I think it's maybe not necessary. But I will show you Mike's table at the end of this video. So we've dissolved 28.4 grams of C6H12O6 glucose in 355 grams of water, and we want to know the mole fraction of glucose in this solution. So I want to know the mole fraction of glucose. So that's going to be the moles of glucose divided by the total moles. And so the total moles is just the sum of the moles of glucose and the moles of water. So I need the moles of glucose, I need the moles of water. So I need the molar masses. So the molar mass of glucose, I have 6 carbons, 12 hydrogens, 6 oxygens, and I get 180.18 grams per mole. I need the molar mass of water. Now, we use water enough, you may already have that memorized, but I'll go ahead and show it anyway. The molar mass of water, 2 hydrogens, 1 oxygen, 18.02 grams per mole. So now I need the moles of each one. So the moles of glucose, I'll take the 28.4 grams of glucose, divide that by the molar mass, and I get 0.158 moles of glucose. I need the moles of water. Divide that by the molar mass of water. And I get 19.70 moles of water. So then my total moles is just the sum of the moles of glucose and water. So my total moles is 0.158 plus 19.70. So I get 19.86. I'm going to keep an extra sig fig. Let's get a little more room here. So then the mole fraction of glucose is then the moles of glucose divided by the total moles. And as you see, the moles cancel in these mole fraction calculations, so the units on mole fraction are that it doesn't have any. It's unitless. So I do 0.158 divided by 19.86, and my mole fraction is 7.96 times 10 to the minus 3. So that is the mole fraction of glucose. All right, so the last two concentration units that we're going to talk about are pretty similar. We have parts by mass and parts by million. In parts by mass, we take the mass of the solute and divide that by the mass of the solution, and then multiply that by a multiplication factor. And so there are 3 types of parts by mass that we're going to talk about, and the only difference between these 3 is what the multiplication factor is. So if I want a mass percent, then I use 100 as a multiplication factor. If I want parts per million or parts per billion, and these are very often used when we have really low concentrations, I just change the multiplication factor. So parts per million, I multiply by a million, 10 to the 6. Parts per billion, I multiply by a billion, or 10 to the 9th. And so, parts per million, parts per billion may seem a little bit weird at first, but they're really just mass percents, where instead of multiplying by 100, you multiply by a million or a billion. I don't have examples with parts per million or parts per billion in this video, but I made a second video with some specific examples using these 2 concentration units. Alright, now parts by volume is basically the same as parts by mass, except rather than taking the ratio of the mass of the solute in solution, we use the ratio of the volumes of the solute in the solution. But we have volume percent, where we multiply by 100, and we can do parts per million or parts per billion using volume by, again, multiplying by a million or a billion. And so whether we're doing parts per million by volume or by mass, they basically have to tell you in the problem. All right, so I'm going to finish with an example. So we're given a bunch of information here, and we're asked to calculate the molality, the mass percent, the mole fraction, and the mole percent. And so when I see problems like this is when I definitely jump to Mike's table. And so before I even look at my numbers, I'm going to go ahead and build a table. And so I need the solute, the solvent, and the solution. And I have volume, mass, and moles. And so when I look at what they've given me, it looks like they've given me some densities, which don't go in the table. They've given me a bunch of volumes, which do. So I've got 20.2 milliliters of methanol and 100 milliliters of water. So the lesser component is the 20.2 milliliters. So methanol is my solute. So I'll put 20.2 milliliters there. We have 100 milliliters of water. And then we have 118 milliliters of the solution. And just like I said at the beginning of the video, you notice that the volumes aren't additive, right? If I just add the volume of the solute and the solvent together, I get 120.2. You see the solution is actually less than that. So you can't just take the volume of the solute and solvent, add them together, and get the volume of the solution. That won't work. In this case, they just gave us the volume of the solution. All right, so let's do these separately, right? Don't get confused by trying to, do all four of these concentrations at once. We're just going to focus right now on molality. And the molality is the moles of solute divided by the kilogram of the solvent. And so when I look at Mike's table, the information I need to get the molality is I need the moles of the solute and I need the kilograms, or the mass, of the solvent. And once I get those two, I can divide them out, and that will give me the molality. So finding the moles of the methanol, the solute, is going to take a little bit of work. Finding the mass of the solvent is going to be not too bad, because they gave me the densities of methanol and water, and I can go from volume to mass using the density. And because the density of water is 1 gram per milliliter, if I have 100 milliliters, I don't even have to do any calculations. I know that that's 100.0 grams. And so I need the kilograms of the solvent, not the grams. So you should be getting good, hopefully, at converting between kilograms and grams in your head. Same thing with milliliters and liters. To go from grams to kilograms, I just need to divide by 1,000. So that's going to be 0.1 kilograms of water. To get to the moles of the solute, first I have to use density to get my mass, and then I'll use the molar mass to get my moles. So I know that density is mass over volume. So to solve for mass, multiply both sides by V, and so the mass is the density times the volume. And for methanol, my density is 0.782 grams per milliliter times 20.2 milliliters. Right, the milliliters cancel, and I get 15.8 grams. All right, so I'm going to put that in the table. All right, and now I need to convert that into moles. So I need the molar mass of methanol. So 1 carbon, 4 hydrogens, and 1 oxygen. So I've got my 1 carbon, 4 hydrogens, and an oxygen. So my molar mass is 32.05 grams per mole. So I'll take my mass of methanol, divide that by the molar mass of methanol, and I get 0.493 moles. All right, so to get the molality, I need the moles of solvent. The moles of solute. I've got that. The kilograms of solvent, I have that. And so I can plug those in to now calculate the molality. And so it's going to be 4.93 molal. All right, I'm going to go to the next slide to work the next part of the problem. All right, so I've left the information in Mike's table from the previous problem. I guess I didn't put the volume of the solution in here. I can go ahead and write that in. And so now we want the mass percent. And we could calculate the mass percent of the solvent, but usually if they just say mass percent, they want the mass percent of the solute. And so for the mass percent, that's going to be the mass of the solute divided by the total mass, or the mass of solution times the multiplication factor of 100. And so the information I need is the mass of the solute and the total mass, right? And I already have the mass of the solute. I just need the total mass. And finding the total mass in moles is easy. I can just add the mass of the solute and the mass of the solvent. Masses are additive. So the total mass is going to be 115.8 grams. So getting the mass percent, then I have everything I need. I can just plug in my numbers. So I have 15.8 grams divided by 115.8 grams times 100. And you can see when we do mass percent, right, the grams are going to cancel. And so the mass percent, like mole fraction and mole percent, doesn't have units. And I get a mass percent of 13.6%. And so you can see another advantage of Mike's table is I'd already found the mass of the solute in the previous part of calculating the molality, and so that made the subsequent problems much easier because I can reuse the information that I found earlier in the problem. All right, let's go to the next slide and we'll do the last two, the mole fraction and the mole percent. All right, so for the mole fraction, and again, they didn't specify the mole fraction of what, and so when they don't specify, it can be assumed that they're talking about the solute. So the mole fraction of the solute is the moles of solute divided by the total moles, or the moles of the solution. And so I already have the moles of the solute. I just need the moles of the solution. And like mass, the moles are additive. So I can just take the moles of the solute, add those to the moles of the solvent, and that'll get me the total moles. So I also need, right, as an intermediate, I need to find the moles of the solvent, the moles of the water, but I can do that. And so once I get the moles of the water, add that to the moles of the methanol, and then we can calculate the mole fraction. So the molar mass of water we've already calculated in this video is 18.02 grams per mole. So, well, rather than writing water, I'll write the solvent. So the moles of the solvent is 100.0 grams divided by the molar mass, and I get 5.55 moles. All right, so 5.55 plus 0.493, I get 6.04 moles total. So then the mole fraction of the solute is 0.493 divided by 6.04, and so my mole fraction is 0.0816, and I guess let me put in the units here, right? The moles will cancel, so the mole fraction is unitless, and so that is my answer for the mole fraction. And we can go ahead and do the mole percent here in the same slide, because to get the mole percent, all I need to do is multiply the mole fraction by 100, convert it from a decimal into a percentage. So the mole percentage is 8.16%. As I mentioned before, I know these problems seem a little bit complicated. Mike's table is a great way to organize these. And if you want another example, I have another video specifically using Mike's table.